All right, hi everyone. Welcome back to CHAMP. Today we have Beihui Yuan from Cornell University, and she's going to tell us about a counterexample to the Schenck-Stiller 2r+1 conjecture on splines.
Oh, hello everyone. So this is the first talk after the New Year, so Happy New Year to everyone. And today I'm going to talk about a counterexample to the Schenck-Stiller 2r+1 conjecture on splines. And this is a joint work with my advisors, Mike Stillman and Hao Schenck. So I am going to talk about what is a spline and why do we care. Also, I'm going to talk about how do we use the commutative algebra tools to study it. And I will present our counterexample to this 2r+1 conjecture. And of course, I will talk about what the conjecture is. And then we will also talk about the future of this topic, of a modification of this conjecture and some open problems. And if you have questions, feel free to interrupt me in the talk because we have plenty of time today, okay? Yeah. So first of all, what is a spline? A spline in a sentence is that it is a set of piecewise polynomials. So to approximate a function over a region in Rn, we may consider a subdivision of that region. And then we put on each of these small pieces polynomials. And also we require some smoothness on these boundaries. And in this case, you will see this is a rectangular region with triangulation. This is one example of how we divide this region. And we call the set of CR differentiable piecewise polynomials on this subdivided region a spline set. And this is our notation for the spline set. Okay. And why do we care? Splines are fundamental objects in numeric analysis and approximation theory, where they are used in finite element method to solve PDE. For example, you can see the picture here. This is a picture of finite element method to solve this function. And this guy is from shape modeling. It is another application of splines. And why do we commutative algebras care? This is because a spline set has rich algebraic structures. For example, you can see that this guy is, first of all, a linear space, right? So it is closed under addition and scalar multiples. And it is also a module over a polynomial ring. And it also has a natural R algebra structure. So one interesting classical result on this side, the R algebra structure side, is by Bellara for a triangulation delta, the continuous piecewise polynomial over this triangulation is isomorphic to the fifth ring of delta. And this is very good because we have a lot of tools in commutative algebra to study this guy, right? Now you may ask, what is CR of delta like when R is greater than 0? Let's see, maybe this is the simplest example, but we will see what is the spline set like. So here we have such a subdivision. It has two faces. And I will assign on this region, H1 a polynomial and H2 another polynomial. So an element in this set should be of the form H1, H2. And also don't forget, we require some smoothness on the boundary. Therefore, the condition should be the difference between these two polynomials is some multiplication of some polynomial with the linear form, this to the r+1 to the r+1s. So the linear form is a linear form which vanishes over here, okay? And this is what an element in CR of delta is like. This example. Next, let's see a little more complicated example. And this example will appear several times in this talk. So let's give it a name. It is called the star of a vertex. So the star of a vertex is something like this, okay? This is that vertex. And in this case, again, we assign polynomials in each of the small regions. And if it is an element in this spline set, it should satisfy 4 conditions in this case, right? Because we have 4 boundaries here. Now, these are the conditions. Now, if you add these 4 equations together, you will see on the left-hand side, it makes 0. And therefore, we have such an equation. That means in this case, these 4 polynomials must satisfy such an equation. So therefore, A1, A2, A3, A4 is the syzygy of the powers of linear forms, right? Okay, so this shows how syzygies enters in this problem. Okay. And we can require smoothness. We can also require an upper bound of degrees of those polynomials. And if we do this, we will denote the subset of that spline set by this, and this D is the upper bound of the polynomial. And this set is still an R vector space, and it is finite dimensional. So in this case, the natural question is, what is the dimension of this guy? Well, it is still an open question, even for planar regions. For example, this conjecture is a conjecture for planar cases, and where R and D is relatively small, right? R is just 1, and D in this case is just 3. And Bellara proved this conjecture only for the generic triangulation. So the more general case, which is if we consider the non-generic cases, it's still unsolved. It's still a conjecture, okay? And for simplicity, for the rest of the talk, let's just focus on planar regions and with triangulation. The good news is in some cases, we do know how to compute this guy if we focus just on such cases, okay? Now let me introduce Shoemaker's formula. The Shoemaker's formula is in terms of R, D, and delta. And here we use, for these 2 things, these are just some combinatoric data of delta. This one is the number of interior edges. And this one is number of interior vertices. And for this little sigma, it again only uses the number of slopes around each vertices. So in most cases, it just uses some combinatorial data of this delta. So then if you have your delta R and D, you will know how to compute this. And what's the good thing here? The good thing here is that sometimes this actually gives you the dimension of our spline set. And this works if delta has no totally interior edge. So you will ask, what does this mean? Totally interior edge. And one example is that so for example, the star of a vertex case. In that case, it just works, okay? And of course, I will tell you what this thing is. So let's introduce some terminologies first. So by looking at this configuration, we call this a generic configuration. That means if I like jiggling these vertices a little, it does not change the result of the dimension of that spline set. Okay, if I just change the position of this guy a little. So, and interior vertices. Let's see, if I index these vertices, like this, then in this case, 0, 1, 2 are interior vertices. So it's not on the boundary, right? Totally interior edges means if the two vertices of that edge are interior. In this case, 0, 1 and 0, 2 are totally interior. But 0, 3 is not. This is because 3 is on the boundary. Okay, any question here? Okay, so another good thing about the Shoemaker's formula is that in general case, the Shoemaker's formula gives us a lower bound. This works in any case. It just gave a lower bound. And in some other cases, for example, if we know the relation between D and R, and in this case, D should be greater than or equal to 4R plus 1, then again, this formula works. Holds with equality, okay? So here comes our conjecture. Because you can see on the last page, the Shoemaker's formula holds with equality if D is greater than or equal to 4R plus 1. So can we have a lower bound? For example, what if D is greater than or equal to 2R plus 1? So Schenck and Stiller conjecture that this actually holds with equality if D is greater than or equal to 2R plus 1. And that is why I call this guy 2R plus 1 conjecture. And here is another conjecture. I just mentioned pages before. These three guys conjecture that for R equals 1 and D is greater than or equal to 3, this equality holds. And you may consider this as a subcase of the Schenck-Stiller conjecture. Because if you make R equals 1 here in the Schenck-Stiller conjecture, then it is just AMS conjecture, okay? However, this conjecture is, this one is conjectured before the Schenck-Stiller conjecture. It appears in about 80s, I think. Okay, so because we want to use commutative tools to study this thing, and especially we want to use free resolutions and CTGs, yeah, that's what I really like. Okay, so I want to have some graded S module. So we want to homogenize this spline module. This is not a graded one, but we want to have a graded one. So we embed over delta in the spline z equals 1 in R3. And we take the cone of the delta with the origin, and we denote this cone by delta hat. Then the homogenized spline module, the notation is this, is a gradient module over Rxyz, that is in 3 variables. And we denote this ring by S. Then we can talk about the Hilbert function, right? The Hilbert function, by definition, is just the dimension of this gradient module at degree D. And it is not hard to prove this equality holds. That is, the dimension of this guy is just the dimension of this guy we want, okay? And we want to present this gradient module, maybe in terms of a kernel of some S module maps, okay? So here, first of all, I want to define a chain complex S bullet. And this chain complex is defined by, we consider the relative homology chain complex of delta with relative to the boundary of delta, and with coefficients in S. And the differential map is the Euro simplicial boundary map. So in planar cases, this chain complex has only 3 non-zero terms: the zeroth term, the first term, second term. We may consider the graded module as the kernel of such a map. Again, this is the number of interior edges, and this is the number of faces of delta. And this map has 2 blocks. One block is just the differential map here in the chain complex. And the other block is a diagonal matrix. And on the diagonals, it is the linear forms to the R+1s. Again, let's use this example to show what this map is like. In this example, you will see the second differential is this part. It's like this. And we have 4 boundaries here. And so we have this linear maps, linear forms to R+1s on the boundary, on the diagonal. Yeah. And next, I want to introduce the mean tool we used to attack the dimension problem. That is called the Bellara's chain complex. It is invented by Bellara, and it is modified by Schenck and Stillman. And that is what we use today. And just 2 pages before, I defined this chain complex. And now we have to define a subcomplex of this guy. Let's call this G bullet. That J of tau, here tau is tau is a interior edge of delta. Let J of tau be defined by a principal ideal generated to L 2r+1, and here again this guy is a linear form that vanish on this edge. And then for every interior vertex, we define J of V to be the sum of all the taus which has a vertex to be V. And then for all I which is greater or equal to 2, we define G sub I to be just 0. And G sub 1 is the direct sum of all the J of taus. So this is a submodule of S1. And G sub 0 is the direct sum of all such J of V's. So this is a submodule of S sub 0. And we can have the map, this differential coming from the S-split. And then this is a subcomplex of S-split. Okay, how do we use it? First of all, let's show what's this like with our example. In this example, G1 is a direct sum of principal ideals. It has 4 terms. So every one of them is a copy of S shifted by r+1. And G sub 0, because we only have one interior vertex here, right? So it is just one copy of an ideal generated by powers of linear forms. And how do we use this? Villara proved that if we consider the quotient complex, because this guy is a subcomplex, right? So you can consider the quotient complex. And in this case, in the planar case, our graded module is isomorphic to the second homology of this quotient complex. And another result here is that Schenck and Stillman gives a criterion for this module to be free. So this module is a free module if and only if the underlying topological space has genus 0 and Shoemaker's formula holds for all degree D. So these two things are obtained by the Bellara's chain complex. And another good thing here is that the first homology of this quotient complex is of finite length. And the Shoemaker's formula holds for equality if and only if this thing vanishes at degree 0. So we know that if a module M is of finite length, then we can talk about the Casanova-Manford regularity of M, which is the greatest degree D such that M does not vanish, right? Therefore, we may just rewrite the 2r+1 conjecture as this. This is the same conjecture. We just rewrite it in terms of regularity of the first homology of the quotient spline. So it may be restated as regularity of first homology of this quotient complex is less than or equal to 2r. And now here comes our counterexample. So our counterexample is a configuration like this, and we also have some coordinates here. Okay, we call this delta sub y. And we claim that for r equals 2, the regularity of first homology is greater than or equal to 5. So this makes a counterexample to the 2r+1 conjecture. Because the 2r+1 conjecture claims that the regularity should be, in this case, it should be less than or equal to 4, right? And if we can prove that the regularity here is actually 5, then it is a counterexample. Okay, so how do we prove it? We use the Bellara's-Spline complex, and then we obtain a lemma. This lemma is a lemma that how do we present this guy? This guy, in this case, is isomorphic to the co-kernel of such a map. It is a 2x6 matrix. And you can see we have 2 0 entries here and also 2 0 entries here. And these are just polynomials. And for each r, we know the degree of these polynomials. And when we know the coordinates of the vertices in our configuration, we can actually know what these polynomials are. For example, using the coordinates we have here, we can write down this map. I transpose it because it is too wide, okay? But the entries are just like this. We can write it down explicitly, even by hand. Now we may compute a gradient basis of the image of this map with respect to position over terms order, where E1 is greater than E2. And these two E1, E2s are the generators of this module. So they are of degree r+1. And after our computation, the result is like this. We have 7 elements, and the last one here, it equals z cubed E2. So we claim that the squared E2 is non-zero in the co-kernel of this map. And then if you compute the degree of this one, you will see it is 2 plus r+1 because the degree of E2 is r+1. So it makes 5. Hence, for dx5, this guy is non-zero. Okay, so this proves our claim here. That means our configuration is a counterexample to the 2r+1 conjecture. Oh, wait. Any questions so far? Okay, now you may wonder, how did we find this counterexample? So actually, there was a paper in 2005, and in this paper, the author shows that for such a configuration, the regularity of this H1 is exactly 2r. And you can compare this guy with our counterexample. So let's see. This is the example here. To get our example, you will just need to remove this edge. You add an edge here and 2 edges here. And the point here is that these 2 edges should have different slopes. And you will get our example. Okay, I just made some modification to this example to get our counter example, because this one is right on the edge, right? It is 2r, yeah. Okay, so then after that, we did some experiments on our configuration, and the computation results of my colleague 2 from for R from 1 to 20 suggests that the regularity of this guy is 9/4R. So it is not just if we can modify this conjecture by putting that, oh, how about 2r plus 2 or 2r plus 10? It is not like 2r plus anything will work. Okay, it is just 9/4. And we have proved that the regularity of this guy is greater than or equal to 2.2r. And how did we prove this one? This one is, recall that we have those, we have such a map, such a 2x6 matrix. And in that 2x6 matrix, there are 4 zero entries, right? So we have moved the 2 entries above these 2 zero entries. We have moved them here. And also on the other side, there are 2 zero entries here. So we move the 2 elements below that thing to here. So we have such a map, and this H1 is still isomorphic to the co-kernel of this map. Now, we can compute, because if we know the smoothness R, we know how to compute these 2 numbers. And also, because A1, A2 here, for example, if we choose the right coordinate, they can be written in only 2 variables. So again, we know how to compute this, the Hilbert function of this guy, and also for this guy. So as a result, we know how to compute the Hilbert function of the target and also of the source. And therefore, we have a bound on the Hilbert function of the co-kernel, which is H1. And we actually get this one. But we really hope we can get this one because it appears in the experiment. Okay, now let's talk about the future of this topic. So first thing is that our example is not generic. So if you here the coordinates, the position, actual position for the vertices is crucial. So maybe if you move these things little, the regularity will change. Okay, so this is a non-generic configuration. So our question is, does the Schenck-Stiller 2r+1 conjecture still hold for generic deltas? And another question is, because our counterexample is not a counterexample to this conjecture. Though this conjecture is on a subcase of the 2r+1 conjecture, our configuration only makes counterexample for R is greater than or equal to 2, right? And in our proof, we use R equals 2. So if you try R equals 1 in this case, this conjecture actually holds. Therefore, can anyone give some counterexample to this conjecture? Okay, and we want to find the smallest number, k, such that regularity of H1 is smaller than or equal to kr. What is the number, right? Okay. And another thing we should consider about is how about higher dimensional such delta? Just now we focus on the planar cases. do we have to stick to planar cases? Why don't we consider higher dimensional cases? Well, if we consider, for example, a 3-dimensional delta, and to study this one, maybe the analogous case to the star of a vertex case is the simplest non-trivial one, right? And for that case, we need to figure out the Hilbert function for ideals generated by powers of linear forms. Using Macaulay's inverse system, we can translate this problem into the problem of determining Hilbert function of fat points. And fat points are just points with multiplicities. So fat point schemes on a plane, and a famous conjecture on that side by these 4 people is still unsolved. So therefore, if you can solve the problem of a 3-dimensional delta on the spline side, you will, that means you just solve this conjecture, okay? You will get result also on this side. Okay, so that means higher dimensional delta, even just for 3-dimensional delta, is very difficult. Okay. So I think I'll just stop here. Thank you.
Thank you. Thank you. Great. Questions? Okay, so I have a couple of questions I want to ask. When you were telling us where your example came from, and you showed us Stefan's example, and then you drew yours and said, "Oh, look, we just changed this a little bit." Yeah. Was this sort of a trial and error, or is there, are there results of the sort like, if you do this change to your delta, that changes the regularity in a certain way?
Oh, so I think the principle here is kind of like if you have more totally interior edges, things will go worse.
Okay.
Yeah, so that's why I just add interior edges.
Mm-hmm.
Okay, and I force them to be in different slopes. That is also crucial. Yeah.
Good.
And also another principle here is that if a slopes around one vertex we have more slopes around vertex, the situation will be better. So to find a counterexample, I want the slopes to be less. Yeah, that's a principle. Yeah.
Yeah, because when you said like more interior points would help, I was thinking, oh, can't you, add more?
Right, have a rather complicated thing here.
Yeah. Yeah, cool. Okay, so the other question I wanted to ask is, in the very beginning when you were motivating the problem, and you told us, one of the first 2 slides, you told us how this is like open in general to compute these dimensions, even in the case, I think you said like C1 degree 3, that was still open. So I've never really thought about these things. So this is a very naive question probably, but what makes it so hard to compute?
So maybe one thing is that even if we fix R and D, we can have many different delta, even on the planar case, right? We can have infinite possibilities. So that's why to solve such a problem is hard.
But you mentioned earlier that there were some classes of deltas for which you know things. How?
Yeah, so it's like if the delta has no totally, so every problem here is created by totally interior edges. So for those configurations has no totally interior edges, this one is solved by the Shoemaker's formula. Yeah, but yeah, but the totally interior edges make the global dimension unpredictable.
Great, thank you. Are there other questions from the audience? Okay, if not, let's thank our speaker again.
Thank you.
Great.